This is probably not something you have at your disposal, and I should have written the number on it, but there was on a homework problem. It had to do with rabbit population increase. And the answer was C times A to the T. Now, does C times A to the T sound like some common formula? What is that exactly?
Exponential growth.
Okay. But like, what would C be?
Some constant.
Equals A.
That's again some constant.
Or C times A to the T.
Yeah, some constant. All right, we're going to get started. Happy Monday. Quick note. My daughter needs surgery. The consultation is the 5th of April, so there will be no class. Hoping we can get the surgery scheduled for after the semester, but we'll see. Going to finish up with the exponential and logarithmic functions. Looking at some applications, just a few. Homework's going to have some more models for you to look at. So you were told a amount P naught is invested at an annual rate of interest R. We want to find how much time, right, how many years it would take for this money, this initial investment to double if interest is compounded n times per year. This is known as the doubling time of the investment. So we start with the model. Remember, compound interest, P equals P naught times quantity of 1 plus R over N raised to the N times T. To double, T would become 2P naught, right? Divide by P naught. 2 would have to be 1 plus R over N to the N times T. We're solving for T. Right, log of 2 would then be log of 1 plus R over N to the N times T. And then using properties of logs, we can write that as NT times the log of 1 plus R over N. So T would be log of 2 over N times log of 1 plus R over N. And that's the doubling time. If we take as an example compounding annually at a rate of 12%, if you get log 2 over log of 1.12, it should be about 7 years. Just going to double check that. Six years. And 6.1, that's 1.2 months. So let's just say 6 years and 2 months. Oh, 10% is, I think, 7 years. Right, so what this means is if you don't touch the investment, you don't make any withdrawals, you don't make any additions, about every 6 years, 2 months, the amount in the account will double. And you can find similar formulas for tripling time, quadrupling time, quintupling time, right?
So what, you want to do quintupling time, it would just be LN5 instead of LN2?
Yep. Radioactive isotope has a half-life of 35.2 years. How many years to the nearest tenth of a year would it take before an initial quantity of 1 gram decays to 0.01 grams? So half-life is an interesting thing. So radioactivity is governed by the laws of quantum mechanics. The number one rule of quantum mechanics is you don't bloody know anything. It's called Heisenberg's uncertainty principle. Half-life is the average amount of time it would take for half of a radioactive isotope to decay. Right, so 35.2 years means after 35.2 years, you would expect half of the radioactive isotope to have decayed. In actuality, it could be longer or it could be less. You just don't know. This has another interesting consequence. Every 35.2 years for this isotope, half will decay. So let's just make it easy. Let's say it's 35 years. Means after 70 years, a quarter remains. Right, 35 years, half decays. After another 35, half of what remains decays. After another 35, half of that remaining decays, which means you have an eighth left. Which means it never actually fully decays. Once radioactivity is introduced in the environment or anywhere, it's there forever. It's just the levels that begin to drop. So Chernobyl will be radioactive forever.
As well, remodel.
And Hiroshima. The only question is how long is it going to take for those levels to reach safe levels where you can actually populate it again.
You still live in the first one you said. I was just watching a documentary of like those dangerous places to live.
What, Chernobyl?
Mhm.
Well, they're living there now, but I promise you they're not the same people.
Some of them, they said that there's only maybe like a handful that are still there, but they're in like their 60s. Saw a couple there.
At ground zero, that's impossible. Ground zero was deadly.
So they show like, they have like a fence where obviously it says like it's fenced off, but they're still in that vicinity of it. And like she said, like her husband, I think, was sick, like he had like some like kidney function issues, but like he was. This documentary was filmed like 2000 and maybe like 3 or 4 years ago.
I have to look at how close it was. Because ground zero was death.
It's called, well, the show on Netflix is called like Most Dangerous Places to Live, and it shows like all of these like radioactive places and.
I'm sure Russia isn't as rigorous about regulating and
So yeah, Russia's not going to give you
protecting the populace.
Russia's not going to give you accurate information to begin with. Same thing with China. If they tell you something, you can probably assume the opposite is true. Since we're dealing with radioactive decay, this is an exponential decay problem. The actual model for exponential decay is what's called an initial value problem. It's a differential equation. We're looking at its solution. You're going to more depth in how you get this solution when you take a differential equations class. So A is A naught E to the KT, where A naught is the initial amount present, right? A would be the amount present after a period of T passed. In this case, it's going to be years. Problem is, we don't know what that K value is without observation. But we have an observation. We have its half-life. So we first have to find that K. Half of the remaining amount after 35.2 years, so half the remaining amount is the original amount, or half the original amount, E to the 35.2 times K. Which of course means that a half has to be that E to 35.2K. I don't know why I wrote 3.52. Means log of a half, which is negative log 2 is equal to 35.2K, and so we have our K. Negative log 2 divided by 35.2.
That's log of 1/2.
Yes. Log of a half is the same as negative log 2. And again, using the properties of logs. Makes sense. Since we're in decay, K should be negative. If it was growth, we'd want our K to be positive. Right? K is called the rate of growth or decay, depending on what you're looking at. So if you take the absolute value of K, log 2 over 35.2, that gives us a rate of decay. Now, A naught, 1 gram, right? So I'm just going to replace A naught with 1. There should be a T there. Yes, there should. Again, using properties of logs, you can rewrite that E to that as simply 2 to the negative T over 35.2. Or if you wanted to, a half to the T over 35.2. Same thing.
That's because e to the power of ln2 will equal 2.
Well, E to the power log X will equal X. So you treat negative T over 35.2 as the constant multiple, which becomes the power of what you're taking the log of.
Shit, I'm sorry. Log of like ln of e to the x.
E, well, ln E to the X and E to the ln X are the same. They give you X. Right, because they're inverse functions. Right, so you had to treat that negative T over 35.2 as your constant multiple. So you can write that as just log of something, which in this case it's log of 2 to the negative T over 35.2. And so they just cancel out and you're left with 2 to the negative T over 35.2. Or like I said, you can also write that as a half, all raised to T over 35.2, right? So there is our model. Now we can go ahead and solve for T. right? Because they want to know how many years it would take for that 1 gram to decay to 0.01. Right? So in exact form, t would be negative 35.2 times log of 0.01 all over log of 2. Before we try and approximate this, does this make sense? By the way, we can also rewrite that as log base 2 of 0.01, right? Does this answer make sense? Without plugging it in.
Oh,
Just looking at it, does it make sense?
well, the log of anything under 1 is negative, right? So it's gonna end up a positive. At least it's supposed to be positive in years,
So it makes sense,
or that much anyway.
right? That's what we're concerned with. Right? If it would have been negative time, would not have made sense. Remember that you're taking the log of something less than 1, which makes it negative. So this value is a negative times a negative, which is positive. If that negative weren't there, then this answer would not make sense. Now you can go ahead and approximate it. $233.86, so on and so forth. They wanted it to the nearest 10th. So 233.9. So it would take about 233.9 years for 99% to decay. Measuring sound intensity, we use what's known as the decibel scale. Right? You should be familiar with that, at least what decibels are. So sound intensity is given by D equals 10 times log base 10 of I over I naught. D is what's known as the decibel level of the sound. I is the intensity of sound measured in watts per square meter. And I naught is that on a different line. Is 10 to the minus 12 watts per square meter. That is what is accepted as the intensity of the smallest audible sound. First, I'm going to rewrite this. Now, I naught, 10 to the minus 12. So we have 1 over 10 to the minus 12. Is 10 to the 12th.
Why isn't it just,
I'm sorry, it should be I naught.
oh, okay. Yes, yes.
So that would be 10 to the minus 12.
Right.
What is the common log of 10 to the minus 12?
Minus 12.
That's the model I'm going to be using. Notice this works because I naught is a constant. What we want to do, calculate the decibel level of a rock concert at an intensity of 10 to the minus 1 watts per square meter. The 120 plus 10 log of 10 to the minus 1. Common log. Common log of 10 to the minus 1. I think they shorthanded this. Decibels.
Yeah. Yeah, it's kind of a funny one.
Yeah, it's because little d has a different meaning if you're talking about prefixes. Little d is 10 to the minus 1, whatever unit that is. I think it's a deci.
Decimeters.
Yeah.
The one that's almost never used. It seemed to go right to centimeters.
So if b is some kind of unit of measure, this could also be read as decibel, deci, whatever b is.
Now, when they say like intensity of 10 to the negative 1 watts per square meter, that's like coming right out of the speaker, like the source. And then it's
Yes.
reduced by distance away from it. So when they talk about intensity, they're talking about the full power
Yes.
at the speaker itself.
The intensity is the source.
Yeah.
How strong is the source?
Please leave that up there.
Calculate the intensity of a sound with a decibel level of 85. So we're going to solve for I. We'll subtract 120. What, negative 35? Divide by 10. Right. And now we have to undo that common log. How are we going to do that?
Such a thing as an inverse log function on a calculator.
There is.
So maybe we're supposed to be able to do this without the calculator.
To the bottom minus 3.
Oh,
Right. Just raise both sides as a power of base 10.
Oh.
Be 10 to the minus 3.5 watts per square meter.
that's a tiny amount of watts per square meter, right? I mean, that's like 1 over more than 1,000.
Right. But for sound.
Yeah, it's just weird to think of an intensity as being such a tiny amount.
Again, it's also only 85 decibels.
So if it was 120 decibels, then it would be 10 log I equals 0. Log I would be 0. And now I'm really confused. What if it was 120 decibels instead of 85? So
The intensity would be 1 watt per square meter.
120, subtract the 120, you get 0 equals 10 log I.
Right. So I would be 10 to
10
the 0.
What power?
The exponent would become 0, wouldn't it?
Oh, so I would be 1.
I would
Oh.
just be 1 watt per square meter.
10 to the 0. Okay, thanks. World record for like loudest concert is somewhere up in the 130s by now. Just absurd.
Which is nothing.
You ain't catching me near those speakers.
Sonic booms have that beat.
Oh, well, I'm sure they do.
Actually, the physics of a sonic boom is pretty interesting.
When I see the name Richter, I think of Total Recall. One of the villains that was apt to get Schwarzenegger.
Thankfully, that's not this Richter.
Ends up getting his arms chopped off.
So when measuring earthquakes, there's actually more than one logarithmic scale that's used. Most common one, they're all called Richter scales. The most common is 2/3 log, common log of E over E naught. R is the magnitude of the earthquake, E is the energy released by the earthquake, and E naught is the energy released by a very small reference earthquake. Again, when we talk about the energy being released, we're talking about at the source. Find the magnitude of an earthquake that releases an energy of 1,000 E naught. We're going to have 2/3 common log 1,000 E naught divided by E naught. If I remember correctly, I'm not sure I do, I think they typically measure the aftershock for E naught.
Again, the subtraction log.
No need. E naught over E naught is 1.
Oh.
We have to simplify.
Is that the whole section?
Well, yes, we're going to keep going, right?
Yeah.
So what is the common log of 1,000? And we know who's going to be answering this question because she walked in late. So what's the common log of 1,000? Common log of 1,000. What does that evaluate to?
Log 1,000. Log 10. Yeah, I just walked in, you just put me on this little.
This is what happens when you walk in late, right?
It's my mom's birthday today. Took out lunch.
You didn't bring me any. That's even worse.
Vegetarian?
No, but I'll eat it. I'm not picky with my food. You just said it was vegetarian, but you had ribs. Okay.
Plant-based ribs.
They're not, then they're not ribs. It's like when they call it veggie, it's not a burger at that point. I'll accept that. Common log of 1,000 is 3. Left with 2 joules. Oh no, I'm sorry. Joules is for energy. We're left with a 2.0 on the Richter scale. I don't think it has any units. Find the energy released by an earthquake that measures a 5.0 on the Richter scale, given that E naught is 10 to the 4.4 joules. So 5 is going to be 2/3 common log of E over 10 to the 4.4. This is where we're going to have to split it. Common log of 10 to the 4.4. It's 4.4. 2 times that, 8.8. Right, this is 8.8 over 3 for now. Adding 8.8 over 3 to both sides. It's what, 23.8 over 3? The 23.8 over 3 is 2/3 common log of E, which means 23.8 over 2 is common log of E. 23.8 over 2 would be, what, 11.9?
23.8.
Yeah.
Yeah. 1.9.
I just realized I could have done the 2/3 first, but could have multiplied by 3/2 before doing any of this. Oh well. Gets me to the same place anyway. Then what's E?
10 to the 11.9 power.
Joules. That's about a trillion. A lot of energy.
This is J.
It's the units of energy, joules. Finally, ratio and energy released by an earthquake that measures 8.1 on the Richter scale, and an aftershock measuring 5.4 on the Richter scale. What we're going to need to do is find a formula for the energy released by an earthquake with a specific Richter measuring. And to start with, R is 2/3 log, common log of E over E naught. Means 1.5 R. Common log of E over E naught. So 10 to the 1.5 R is E over E naught. Let's call E sub R. Is E naught times 10 to the 1.5 R. All right, so this is the energy released by an earthquake that has a magnitude R on the Richter scale. We want a ratio of an 8.1 magnitude to a 5.4 magnitude. That's what we're looking for.
Find that?
Mhm.
Okay.
One and a half times 8.1.
Well, 5.
Yep. One and a half of 5.4.
Eight 8.1.
8.1. 12.15 minus 8.1.
It's gonna be 10 to the 4.05, right?
Here's your ratio.
It's that many times more intense.
Well, intense energy.
Okay, yeah.
What this means is an earthquake with magnitude 8.1 releases 10 to the 4.05 times more energy than a 5.4 magnitude earthquake. That's slightly over 10,000 times the energy. Right? The logarithmic scale, not a linear scale.
You teach, during the summer. You, I think the way, like this going sessions.
There's me.
You teach.
I probably will because I'm requesting to not come on campus at all over the summer. But we'll see. I just signed in. What's your problem? Told you this was an easy unit.
Well, it was till today.
Okay, look, I'm signed in, so. Don't know why you're giving me a problem. Signed in. You always do this. It's because of this.
I hadn't checked yet today, but is test 2 done?
Whatever. I'm not signing back in. You'll upload, I know you will.
Oh, wow, yeah. I mean, just do next Monday. I just put 2 and 2 together in my head, okay?
Maybe I'll give you my Calc 3 test. See how many people get that one. Test 3 is now available. Right, covers exponential and logarithmic functions. In my opinion, probably the easiest test. Can I? Don't know. I mean, you have access to it, so you don't really need me to, right? All right, as before, complete the test on loose leaf paper. When finished, you will upload it as a single PDF file. I don't remember if there's anything that require graphing. If a graph is required, screenshot can be uploaded separately as JPEG.
Even the way I uploaded the last test.
I haven't even looked at test 2 yet.
Okay, so like when you say single PDF file, let's say like I took up multiple pages and I took multiple pictures and then I upload pictures of those pages, but it's not on one little thing. That's like,
It has to be converted to a single file.
If you open up your notes on my phone, there's a scan feature on there. So open your notes and then open up a new thing. And then at the bottom should be a camera. Click on the camera to scan document. And then if you take a picture of that, it actually scans it.
and I can take multiple
And
and then save. Okay,
Right.
so if I re-upload it as one single PDF, would you still accept it?
like this is not mine. And
It's going to be flagged late, so probably not. Make sure you upload it without deleting the original uploads, so that you don't get flagged as being late. Allowed to use notes, textbook, other official course material, and any model graphing calculator that does not have symbolic manipulation capabilities. That means no CAS. Perhaps you're not allowed to discuss this with anyone, not allowed to Google the answers. All right. We'll be due before our April 3rd meeting. And as always, have fun. You wish. I don't know why you'd wish that.
The units,
5.
and this is a 4. Maybe dog. I'll see you again for Precalculus.
We now start what is my favorite topic. We start trig. Trig is broken into 2 units. We introduce the trigonometric functions. There are 6 of them. We also introduce the 6 inverse trigonometric functions. Then we look at what's commonly referred to as analytic trig, which is what a lot of people think of when they hear trig. And so that involves solving equations with trigonometric functions, the trig identities, reducing trig functions, fun stuff. Trig is awesome. There's actually 3 branches of trig. There's rectangular trig, which is what we look at. There's hyperbolic trig, and then there's spherical trig. Hyperbolic and spherical. We look at the rectangular. So that's trig in the Cartesian coordinate system. Trig deals with angles. This is typically what we think of when we think of an angle. This is an angle in standard form. O is your initial point. Let's call this P. That would be called your terminal point. All right, that is a ray OP. Standard form is your initial point is at the origin. And the angle is measured with respect to the positive x-axis. Two units of measure for the angle: degrees and radians. This is an important note. Unless otherwise specified, angles are always measured in radians. By the way, your calculator has 2 modes, degree and radian. Make sure you're in the right mode for the problem. Well, if you have the calculator, I recommend it's easy. Depends on your calculator.
Be mode.
You have to actually go into settings. However, on the Inspire, it's literally right up there. Right now it's in radian. If I click it, now it's in degree. Click it again, back in radians. Otherwise, you have to go into your settings where you go to change your decimals.
It is. Do you have a TI-84? I went to mode and I'm scrolling down and I just got to something radian versus degree, and it's currently in degree mode. So let me see if I hit enter for radian. Oh, yeah. So it's mode. If you scroll down, you can get to it.
I think there's an easier way. I just don't remember it. I haven't used that calculator in decades.
That wasn't too hard. Did you find it? Yeah. All right, cool.
So use it.
Realize I'm required by law to report that.
This one is still set to 2001, so.
Someone admits a crime in front of you, required by law to report it.
It's strong words. I still talk to a guy in the council there too.
2030.
No way.
Two ways to look at trig: circle and triangle. We start with the circle. How many degrees are in a circle? One full revolution of a circle is 360 degrees. Do you happen to know how many radians that is?
Pi.
It's 2 pi. That means 360 degrees is equal to 2 pi radians.
What do you use for the radian symbol? So it's not to look like pi r.
Well, r is radius if you're looking at circumference. Technically, radian is unitless. So you don't write it. That's a pi. It's 2 pi. 180 degrees is equal to pi. One degree is pi over 180 radians. One radian is 180 over pi degrees. These are your conversions. And that's 180 over pi degrees. Let's express 30 degrees in radians. Right, so it's 30 degrees. Times pi over 180 degrees. What we're doing is called unit analysis, which if you've taken any type of science course, you are familiar with. It's one of the first things they teach you in every science course is unit analysis. The degrees wind up canceling out. We're left with radians, which is what we want. So what's 180 or what's 30 over 180? So 30 degrees is pi over 6 radians.
So we can solve this on a calculator.
Technically. Well, be careful, because I don't want decimals. I don't want decimals. So if you put in 30 over 180, it's not going to give you 1 over 6. It's going to give you 0.16 repeating.
Then you can convert it on the calculator.
Yeah, that's more work than just knowing that 30 over 180 is 1/6.
Just wondering if it was on.
It is, but it's going to take you longer than. $135 over 180. Three quarters. We have 3 pi over 4 radians. Oh joy, now comes the fun part. There are two ways of representing degrees. What's known as DMS, degree minute second, or decimals. Yes. This is read as 25 degrees and 30 arc minutes. Yep.
$60 minutes in a degree. 60 arc, yeah.
1 degree is 60 arc minutes. One arc minute is 60 arc seconds. Which means that 1 degree is 3,600 arc seconds. "25 degrees, 30 arc minutes." It's 25 degrees plus 30 over 60 degrees. All right, so 30 arc minutes is half a degree. So 25 plus a half, 51 halves.
Couldn't we just call it 25.5?
As a general rule of thumb, if they give it to you in DMS, you don't use decimals. Otherwise, they would have written it as a decimal. Oh, we're not done yet, though. Never to multiply that by pi over 180. Yeah, 1 degree is 60 arc minutes, which means 1 arc minute is 1/60th of a degree. So that is what, 51 over 360. Both 51 and 360 are divisible by 3. So we get 17 pi over 120. Yeah, because 30 over 60 is a half, right? So 25 plus a half. Common denominator is 2. 25 times 2 is 50 plus 1 is 51. Let's go. So personal preference for me is, unless I'm forced to, I just represent degrees as decimals. Because I hate DMS.
So in other words,
But that's just something that has to be taught. Because some people prefer the DMS system.
You're gonna get one hell of a denominator if you do.
Oh, I know.
Seconds.
This is why I never use DMS. Well, first off, I don't ever work in degrees. I work in radians. That's the standard. Radians are the standard unit. And of course, the math community, the science community works in standard units only. It's always the bloody engineers that have to be weird and make things difficult. Because engineers work in the empirical system.
Yeah, but when astronomers aim their telescopes, they're still doing like degrees and arc seconds and.
Different. Yes, it's different units of measure. They're not measuring angles. They're using that as a measure of distance.
All right.
Right, that's essentially they're doing the parallax. Which has to do with angles, but you're not measuring like an actual angle in the sense of angle you're thinking of. It's measuring it with an angle with respect to like another star or something.
Mm-hmm.
Or the horizon, I think, is how they do it, and they somehow do distance. Again, I don't really work with that. I work in light years for distance. But yeah, there's also degrees, arc minutes, and arc seconds in astronomy, but that's different from this kind of angle measure. But they have the same idea. "42 degrees, 24 arc minutes, and 35 arc seconds." We're going to get 42 degrees plus 24 over 60 degrees plus 35 over 3,600 degrees. No, they close at 4. I think they close at 4. Registration, I know, closes at 4. Pretty sure it's 4 o'clock. I think they run 8 to 4. It's clearly 6,107 over 144. Oh, but the fun's not over yet. Now we get to multiply that by pi over 180. I think 6,107 is prime. Which means you're not going to be able to simplify anything. So it's 144 times 180.
There are people out there that seriously will leave this in fractional form.
Well, let's be fair. The people that are using DMS are not going to convert it to radians.
Oh.
6,107 pi all divided by 25,920. That's the radian measure.
Which makes sense because 6,000 divided by 25 is. Oh, wait a sec. No, it doesn't make any sense at all. I'm sorry. I thought I was relating it back to roughly 40 degrees. No. 80. Oh. Radians, 2 pi radians. Oh, yeah, 2 pi radians is a whole circle. That's about 1/4 pi. So
Slightly less than, yes.
So it's a little bit less than 1/8 of a circle, and 1/8 of a circle is 45, so that's 42. So, yeah,
Yeah, 45 degrees is pi over 4.
and that's
Which
that's
is,
the
yeah,
balance.
it's slightly less than.
So it actually does
Slightly less than pi over 4. Thankfully, this is
Easy enough.
decimals.
Better.
Question. So you said the 1 degree equals, um, the 60 arch minutes. And then what is, how do you get to 3,600 from that? I know, I heard you say it.
1 arc minute is 60 arc seconds. And that means that there's 3,600 arc seconds in a single degree. Think of degree as hour. There's 3,600 seconds in an hour. If they're going to go with this, they should have just called the degree the arc hour, but what do I know? No, which I did because I'd go back in time and stab him before he invented it. So there are 2 ways on which we can do this. There is a more accepted way, and that's to leave pi alone. So just be 165.7 divided by 180, and then multiply that by pi.
Why are we dividing it?
Because we're multiplying by pi over 180. We're leaving pi alone, so it's 165.7 divided by 180. This brings in the idea of something else you are all familiar with if you've taken any kind of science course. The idea of sig figs. Technically speaking, there are only 2 sig figs in this problem. .165.7 is 4, 180 is 2. Technically speaking. However, pi over 180 is a conversion. We know that there are exactly 180 degrees in pi radians. So that 180 is actually 3 sig figs. There should be a decimal point after that 0, which makes it 3. So working with 3 sig figs. That means our answer needs to be in 3 sig figs. 0.921.
Does she use the lower number of significant figures from the fraction?
Yes. And when you add or subtract, you use the highest decimal points. Which is weird, but that's the rule. So if we were adding these, we'd have 1 decimal point. We'd only got the 1 decimal point. Regardless of number of sig figs. I didn't invent the rules. This is the accepted way of writing it. Right, you just leave pi alone, you write that as 0.921 pi. What you could also do is actually throw pi into your calculation. And then again, you'd go to 3 sig fig, so it'd be 2.89 radians.
And those are both correct answers.
Yes. Notice I did not use 3.14 for pi. I used the actual pi command.
Yes.
You never want to use approximations in your calculation. The more you approximate / round in a problem, the more error you begin to accumulate. So you always save it for the very end. That reduces your error. Three sig figs. So it'd be 2.89. And rounding rules are also really odd. Right, below 5, it's, you just cut off. Above 5, you round that digit up. If it's actually 5, you have to look at the next digit. Even rounds up, odd rounds down. So technically, I should have kept that at 0.920. Because what's after that 0, 5, and what's after that 5 is an odd number. So it stays at 0. That's what's usually used, but right, that's when you really start to get there's more rules that are used.
Yeah. Because
The rule that I've always used is if it's exactly 5 because it's half, you have to look at the next digit. Yeah, that's usually but in more advanced, there are other rules. Again, because it's exactly halfway. Right? If you're below halfway, you keep it the same. If you're over halfway, you round up. If it's exactly halfway, what do? You have to look at the next digit. And then it's even odd. I think there's also a rule that says if the next digit is below 4, you keep it. If it's above 5, you round, and if it's exactly 5, you go out again. So here we'd have fun because it's 5 repeating. So basically just, oh, that's fun. I'm not using that rule, but that is a rule. This is our first look at a negative angle. The negative angle tells you how you're moving. So negative means we're measuring it with respect to the positive x-axis in the negative direction, which is the clockwise direction. So that'd be 3.85 degrees below the positive x. There's again 2 ways of doing this. The more accepted way is to leave pi alone. So we're going to look at negative 3.85 divided by 180. We have 3 sig figs. Okay, there you go. All right, going out to 3 sig figs. We have negative 0.0214. Leading zeros are not significant. Trailing zeros are also not significant unless there's a decimal.
Wow. So like 0.000,
Those are not.
like 5.000. That's
1 sig fig,
right.
5 sig figs.
That's acceptable to just put a
Yep.
decimal point with not even anything in the
Yep.
10th? What if you put a 0 in the 10th place? Would that make it
No,
6?
just 5 sig figs.
That's a trailer?
That last 0 would be trailing because it's after a decimal. So that's not a significant. Right? These have 2 different meanings. That means we're short 10,000 up to the 10,000 units. This means we're shorts 10,000 down to the single.
That's how we can leave it.
You typically want to leave pi alone. We're going to want negative 205 divided by 180. So it's obviously going to be negative. And we do not want decimal form. Do you see a decimal? So these are exact. There's no decimals, you always keep it in an exact form.
Just cancel out 5.
Which leaves you with what?
Negative 41 over 36.
Negative 41 pi over 36. Fucker. Negative 18 degrees and 30 arc seconds. Negative quantity of 18 degrees plus 30 over 3600 degrees. Which is what, 1 over 120? 18 times 120. 1200 plus 8 times 120, which is 960. So that'd be 2160.
2160.
Oops, I don't know why I did 60 because I'm adding one to it. Negative 2161 over 120 degrees. Times that by pi over 180 degrees. 2161, I believe, is also prime. or 120 times 180. It's going to be the same as 12 times 18, then all times 100. 12 times 18.
Didn't you just do? Yeah. We did, yeah, 12 times 18,
Yes.
216.
Now times that by 100. And there's 120 times 118, or 180. 2,161 pi all over 21,600.
Which makes sense. Teeny tiny bit off from 1/10 of a radian, which is what 18 degrees would be, right?
Yes.
Oh, but what about the negative?
Oh, yeah, it should be a negative. I just forgot it. Oh, thank goodness, decimals. Two sig figs. Negative 0.21 over 180. Negative 0.0012. Should just skip this entire part. Why you'd want to do this, I have no idea, but now we're going to convert radians to degrees. And it doesn't tell us to represent the degrees in DMS, which is nice.
Yeah, that would be horrific.
Pi over 3 would be pi over 3 times, now unit analysis. There's 180 degrees on a single radian. Since we want degrees, degrees goes in the numerator. So multiply 180 degrees over pi. Pi's drop out, that's nice. So what's 180 divided by 3? 60 degrees is pi over 3 radians. Hey,
Here's what we're seeing.
There's nothing inherently wrong with thinking about it as pi over 3 divided by 2 pi to show what fraction of the circle it is, and then take that fraction of 360. Because 2 pi is the whole circle, right?
well, I mean, that's exactly 180 over pi then.
You know,
Right, 'cause you're multiplying by 2 pi and then multiplying by 360.
Good point.
Or
Yes, I'm making more work.
you're dividing by 2 pi, right?
Yeah, 1 pi over 3 divided by
Yeah,
2 pi.
and then multiplying by that by 360, which is the exact same as 180 over pi.
Okay.
Same conversion.
Yeah.
Yes. 5 pi over 9. Which is what? $180 over 9, that can be simplified. What's 18 over 9? Multiply that by 10. Then multiply that by 5.
You divide them.
And by the way, it's also not 4, that's 5. No, 20 times 5. Oh, I'm thinking 25 over 5. Yeah, 20 over 5 would be 4. No, it's times. What's 20 times 5? 5 pi over 9 is 100 degrees. This just popped into my head because of this. Happen to know what the standard unit of measurement for temperature is?
Kelvin?
It's Kelvin. Which, by the way, is just Kelvin, not degrees Kelvin.
Not plural Kelvins.
Nope, just Kelvin. We use that because 0 Kelvin represents absolute 0, the lack of heat. You can't go below 0 Kelvin. If I'm not mistaken, 273 Kelvin is 0 centigrade, which is the freezing point of water.
Those football players that were showing out before the playoff game can handle that.
What?
There was, I think it was the Chiefs. It was like 20 below at the playoff game, and they came out pre-game with no shirts
In
on.
centigrade or Fahrenheit?
Well, either way, it was absurd. It would,
Well, there's a huge difference.
well, but it was,
20 Fahrenheit is a lot, negative 20 Fahrenheit is a lot colder than negative 20 centigrade.
well, either way, it was ridiculously super freezing cold, and they were out there with no shirts on, just warming up on the field. That was like some serious toughness on display. I mean, it was below freezing, let's put it that way. The exact temperature, I don't know. It was below freezing, and they were out there shirtless.
Yeah,
So,
I'm
it
not
was-
impressed.
I was.
I'm not impressed. They're running around, which warms up their temperature. I spent 5 years working in an industrial freezer where it was negative 40 Fahrenheit.
Did you have clothes on?
Yeah, but I didn't wear a coat. I just had short sleeves and shorts. No, I actually like the cold.
You like cold?
I had to because the coat would get in my way. Well, would it be called the metric system? That has specific meaning. I mean, you can, but there are certain values you have to keep in mind. Like 1 second has an actual definition. 1 meter has an actual definition.
That 2/5 has got to have a pi in it, right?
Nope. It's 2/5 radians. Doesn't have to have pi. (180/5) times 2 in degrees is 72/pi degrees. That day. No quiz.
Oh,
We will pick up here on Wednesday.
How about you make it a take-home quiz and we'll all bring it in?
No, because I hadn't actually covered what I need to do the quiz.
Thank you. Reading slow.
However, depend if I can get through everything I want to get through, there'll be 2 quizzes on Wednesday. I think you have a makeup, right?
Thank you, good sir. I'll see you Thursday night.